All right, let's jump right in. Today, we're getting to the very heart of chemical bonding, digging into a concept that basically dictates how atoms interact with each other. We're talking about electronegativity, but I want you to think of it in a simpler way. It's the ultimate chemical tug-of-war.
Have you ever wondered why water is, well, water? You know, this bent, polar molecule that dissolves just about everything, while something like carbon dioxide is a perfectly straight, nonpolar molecule? The answer to these huge fundamental questions all comes down to the forces at play inside the chemical bonds themselves.
Yep, that's really it. You can imagine every single chemical bond as a tiny battlefield where atoms are fighting for control over the electrons they're supposed to be sharing. And the outcome of this microscopic tug-of-war? It determines everything from the shape of a molecule to how it's going to react. So, let's figure out how this battle really works.
So here's our game plan. We'll start by defining what this tug-of-war actually is. Then, we'll see how it leads to polarity and something called a dipole moment. We'll figure out how to predict the winners and losers using the periodic table, and then we'll actually get into the math with Linus Pauling's original method. After that, we'll apply what we've learned to a pretty tough problem and finish up with the key takeaways.
Okay, so let's get a proper definition for this whole atomic power struggle. What exactly is electronegativity?
Well, the classic definition comes from the legendary chemist Linus Pauling. He described electronegativity, that's the Greek letter chi, by the way, as the power of an atom, and this is the key part, within a molecule to attract electrons to itself. See, it's not about some lonely, isolated atom. It's all about how that atom behaves when it's already in a bond. It's a direct measure of its electron-pulling power.
And to make this whole idea useful, Pauling came up with a scale. It's a relative scale, so there are no units. He just set the value of 4.0 for fluorine, which is the undisputed champion of electronegativity. It has the strongest pull on electrons, period. And on the other end of the spectrum, you've got cesium and francium, way down around 0.7. They're the weakest, the ones most likely to just give up their electrons. Pretty much every other element fits somewhere in between.
So now that we know the rules of this tug-of-war, let's talk about the results. What actually happens when one atom pulls harder than the other? This is where we get into these huge concepts of polarity and dipole moments.
This tug-of-war really creates a whole spectrum of results. On one end, you have a nonpolar covalent bond, like in a chlorine molecule. Here, you have two identical atoms, so they pull with exactly the same force. It's a perfect tie. The electrons are shared perfectly equally. But in the middle, you have a polar covalent bond, like in hydrogen fluoride. Here, fluorine is the heavyweight champ. It pulls those shared electrons way closer to itself, which creates a partial negative charge on the fluorine and leaves a partial positive charge on the hydrogen. And then you have the extreme case, sodium chloride. Honestly, this isn't even a tug-of-war. Sodium just forfeits the game and completely hands over its electron to chlorine. That's how you get ions.
Now, this is a really crucial point. Bonding is a spectrum, not a bunch of separate boxes. You might see a textbook that says, a difference in electronegativity of 1.7 or more means it's ionic. But that's not a hard and fast rule. Take lithium hydride. It has a smaller difference, but it behaves pretty ionically. Meanwhile, hydrogen fluoride has a huge difference, but we still call it a polar covalent bond. A much better rule of thumb, if you have two nonmetals bonded together, it's going to be covalent.
To actually put a number on this polarity, we use something called the dipole moment, which we represent with the Greek letter mu. It's just a measurement of how separated those positive and negative charges are inside the bond. You calculate it by multiplying the size of the charge, Q, by the distance between the charges, D, which is pretty much the bond length. The bigger the dipole moment, the more polar the bond is. Simple as that.
So, how are we supposed to know which atoms are the strong ones without just memorizing the whole scale? Well, luckily for us, electronegativity follows some really predictable patterns on the periodic table. Let's look at the rules of the game.
The two big trends are pretty straightforward. As you move from left to right across a period, electronegativity goes up. As you move down a group, it goes down. So why does this happen? Well, think about it. As you go across a period, you're adding more protons to the nucleus. That stronger positive charge pulls harder on the bonding electrons. But as you go down a group, you're adding whole new shells of electrons. This does two things. It increases the distance from the nucleus to those outer electrons, and the inner electrons create a shield, blocking the full attractive force of the nucleus. Both of those things weaken the pull.
Okay, but here's a twist. An atom's electronegativity isn't some fixed, unchanging number.
It can actually change depending on its chemical environment. For one, a higher positive oxidation state makes an atom more electronegative. An iron 3+ ion is way better at pulling in electrons than a neutral iron atom. Second, hybridization makes a huge difference. An s orbital is closer to the nucleus, so the more s character a hybrid orbital has, the more electronegative that atom becomes. That's why an sp carbon is more electronegative than an sp2 carbon. And finally, its neighbors matter. A carbon attached to 3 super electronegative fluorines is going to have its own electronegativity jacked up.
So, we've gone over the trends and the rules, but how did Pauling actually get the numbers for his scale in the first place? Well, his method was absolutely brilliant, and it was all based on something you can actually measure in a lab: the energy it takes to break a chemical bond. Pauling's logic here was just so clever. He said, okay, imagine a perfectly covalent bond between two different atoms, A and B. He figured its strength should just be the average of the AA and BB bond strengths. But then he compared that expected value to the actual bond energy that was measured in experiments. And what he found was that the real bond was always stronger than his purely covalent prediction. So why? Well, when one atom pulls the electrons closer, you get those partial positive and negative charges. That adds an extra bit of electrostatic glue, like tiny magnets, making the bond more stable and harder to break. He called this extra stabilizing energy delta, and he realized it was a direct measure of the bond's ionic character. Let's look at the classic example, hydrogen fluoride, or HF. The bond energy of HH is 435 kilojoules per mole, and for FF it's 158. The expected pure covalent energy for an HF bond, the geometric mean, is about 262. But look at the actual measured bond energy for HF. It's a massive 565. That huge gap between 262 and 565, that's the extra ionic energy, delta. Fluorine's intense pull on those electrons makes the bond way, way stronger than you'd expect.
And all of this led Pauling to his famous equation. He figured out that the difference in electronegativity between two atoms is proportional to the square root of that extra bond energy, delta T. The 96.5 is really just a conversion factor to make the units work out when you're using kilojoules per mole. So by setting a baseline for one element, hydrogen, he could use this exact formula to build out the entire scale, one bond at a time.
Okay, theory is one thing, but the real test is seeing if we can actually apply it. Let's see if we can use everything we've just learned about oxidation state, hybridization, and all that to solve a classic kind of chemistry problem.
So here's our challenge. We need to arrange these 4 species in order of the increasing electronegativity of the central nitrogen atom. We've got ammonia, the nitrate ion, nitrogen trifluoride, and the nitronium ion. Where do you even begin with something like this?
All right, to crack this, we have to look at all those factors for each nitrogen. Now, the trick is to look at hybridization first, because that often has the biggest impact. Let's start with the nitronium ion NO2+. It's linear O-N-O, which means that nitrogen is sp hybridized. That's 50% S character, the most it can have. Next, the nitrate ion NO3-. It's trigonal planar, so the central nitrogen is sp squared hybridized. That's 33% S character. Then we have ammonia NH3 and nitrogen trifluoride NF3. Both of those have a nitrogen that is sp3 hybridized, only 25% S character. So right away we know the sp nitrogen in NO2+ is the most electronegative, followed by the sp squared nitrogen in nitrate. Now we just have to sort out the two sp3s. In ammonia, nitrogen has a -3 oxidation state, but in NF3 it's bonded to 3 crazy electronegative fluorines, giving it a +3 oxidation state. A higher positive charge makes an atom more electronegative, so the nitrogen in NF3 pulls harder than the one in NH3. So, putting it all together, the final order of increasing nitrogen electronegativity is ammonia is the lowest, then nitrogen trifluoride, then the nitrate ion, and finally the nitronium ion is the most electronegative.
Phew, that was a tough one, but it's a perfect example of how all these rules have to work together. So let's just wrap this up with a quick summary of the most critical points you need to remember. Think of this as your playbook for mastering electronegativity. Okay, here's the quick rundown. Remember, electronegativity is the chemical tug-of-war. The outcome of that war determines bond polarity. It follows clear trends. The champions live and up to the right on the periodic table. And critically, an atom's pulling power isn't fixed. It changes with its charge and its hybridization. And finally, remember, this isn't just some abstract idea. It's a real quantity that comes from measurable bond energy data.
And just so you know, Pauling's scale isn't the only game in town. Other scientists, like Mulliken and Alfred Roshaw, came up with their own scales based on totally different atomic properties. Mulliken used ionization energy and electron affinity. Alfred Rushaw used effective nuclear charge. They all basically tell the same story, but they get there from different directions, which is pretty cool when you think about it.
So we've spent all this time focused on the pull within just one bond. But of course, molecules are these big, three-dimensional things, with lots of bonds all pulling in different directions. So that leaves us with one last question to chew on. Now that you can predict the pull of an atom and the polarity of a bond, how do you think that unequal sharing of electrons might influence the overall shape of the molecule itself? That's a story for another time. Thanks for watching.